Chapter 13 is about gases. It's one of my favorite chapters. Why should we even study gases? Studying gases helps us to understand some real-world phenomena, and I'll try to point some of those out to you as we go along. It also gives us an understanding of how science works, because the experiments that people did with gases back in the 1700s and stuff were very simple. They didn't even have electricity back then. They didn't have fancy equipment or anything. They had simple pieces of glassware and very creative minds. And so it helps us to understand how science works. So reviewing the properties of gases. Gases fill their container uniformly, and this is different than liquids and solids. However big the container is, the gas will expand to fill it, a little bit like homework. It expands to fill the amount of time that you have to do it in, right? Or any other thing that you don't want to do. Gases mix completely with other gases, and that's not true of liquids and solids. And gases exert pressure on their surroundings. So they uniformly fills any container, mixes completely with any other gas, exerts pressure.
They exert pressure by themselves.
Yes. Yep. What is pressure? Okay, so another little foray into physics. Pressure is defined as a force over an area. So let's talk about that for a minute. I end up using different examples, and some of them are better than others. So my daughter Emily weighs about 90 pounds, so she's no lightweight. She's a strong girl. So if she comes and I'm laying on the floor and she sits on my stomach, she doesn't have a huge butt, but it's reasonable size. Is that going to hurt? No. I'll feel the pressure, but her force, which is her weight, is applied over a reasonable amount of area. So if an elephant came and sat on my stomach, same amount of area, but like a ton, that would hurt a lot more, right? Because more force on the same area, more pressure. Or if Emily put on some stiletto heels, which I would, she will not do that as long as I'm alive, and stood on my stomach on one heel, she'd probably punch a hole in my stomach. A 100-pound woman walking on stiletto heels can punch holes in linoleum because you have 90 pounds on a 1/4 inch by a 1/4 inch. That's 1/8 of a square inch. So that's 800 pounds per square inch of pressure. So pressure is not only the force, but it's over what area. Okay? So units of pressure, the SI unit is not very useful. It's a Newton per meter squared. Newton is a unit of force. Square meter is a unit of area. This has a special name. It's called a Pascal. There may be some conversion problems where you have to use pascals. The one we use a lot in chemistry is called a standard atmosphere. Its abbreviation is ATM, not to be confused with an automatic teller machine. There's no money involved here. An atmosphere is 101,325 pascals. So a pascal is a very small unit. What is an atmosphere? We know what the atmosphere is. An atmosphere of pressure is normal atmospheric pressure at sea level. So they just say, okay, because everything, a lot of things are relative. So how do you decide, where to place your value here? So at sea level, normal atmospheric pressure, that's 1 atmosphere.
Is that higher or lower?
If you go higher in elevation, you're getting closer to the edge of the atmosphere, and the pressure is less. And if you go below sea level, which isn't possible too many places, but Death Valley is one of them, then the atmospheric pressure is a little bit higher. Two other units that we use in chemistry a lot will make sense after I explain them. Millimeters of mercury. Like, that's weird, huh? A length of an element. Fine. Okay, whatever. 760 millimeters of mercury. That's the same as an atmosphere. 760 torr. This is just another name for this unit. So a barometer. You've probably heard of barometers. We mentioned them the other day. We've got digital barometers on the wall. This is an illustration of the original barometer. So a guy named Tortelli was playing with mercury. Be interesting to see, did he live as long as he was supposed to live? Mercury is really fun because it's really dense and it's a metal and it's liquid at room temperature. And just how crazy cool is that? But sadly, it's also toxic, and so we can't play with it. With your bare hand. Yeah, if you protect yourself, you could play with it, but anyway. So what Tortelli did is he took a glass tube and filled it with mercury and very carefully tipped it over into a dish of mercury. And you may have done things like this as a child, playing with cups and things in the bathtub or in the sink. My kids love to do this. So if you do this with a cup of water, the water stays in the cup. Have you noticed that? You tried it at home. An easier way, instead of tipping it over, is to fill the cup underwater and bring it up upside down. A clear cup is best because you can see that the water stays in there. And it's like, cool. Why does the water stay in there? Well, the water stays in there. The mercury stays even partially in this tube because the atmosphere is pressing down on the mercury and is trying to push it up this tube. Mercury is a lot more dense, though, than water. And so the mercury is pulled down by gravity, and it's pushed from here, it's pushed up by the pressure of the atmosphere. And so the mercury will go to a height where the force of gravity pulling down on it is equal to the force of the atmosphere pushing up on it. Because it's so much more dense, it's actually at a level that we can see. Well, the height of a column of mercury at normal atmospheric pressure is 760 millimeters. And so that's where that unit came from. So he's like, oh, cool, this is really interesting. And so then, you think, how did these people get these ideas? So he takes his little unsteady mercury apparatus and he takes it up the hill. He climbs a mountain with it. Who thinks to do that? As he climbs the mountain, the level of mercury gets shorter and shorter and shorter because the atmospheric pressure is less. Less pressure here, gravity's the same, and so the column gets shorter and shorter. And you can measure it with a ruler. Easy. Then he brings it back down, and as he comes back down, it goes back up, and it's the same height when he gets to the bottom. Oh, all kinds of ideas and thoughts you can do with that. This is part of understanding how science works, right? You think about it. These guys knew so little, and yet they figured out so much. He didn't know what atoms were. They were still arguing about what elements and is it air, earth, water, and fire, or, really weird ideas they had because they didn't know. But he's doing this experiment. It's pretty cool. So the atmosphere presses down on the dish of mercury and supports it up here. What you have up here is a vacuum, empty space. If you did this with water, the height of a column of water that the atmosphere can support is about 10.3 meters, or 34 feet. So there's a good reason not to make a barometer with water. 34 feet is really tall. Good luck even getting that into the classroom, right? Way too tall. So this is a barometer, and that's where that funky unit came from. Let's just go back for just a second. And so 760 millimeters of mercury, and then to honor Tortelli, they created a unit, torr. 760 torr. And that is the same. A millimeter of mercury is exactly the same as a torr. It is pretty awesome. Okay, there's another type of device for measuring pressure called a manometer. Excuse me. A barometer measures atmospheric pressure. A manometer is similar in idea, but it measures pressure of a gas in a container. So here we have gas in a closed container, and it's connected through a bent tube of glass to the atmosphere. And in this tube is mercury. If the pressure in the container and the pressure in the atmosphere were equal, like if you just had an open tube with mercury in it, where would it go? It would just go to the bottom, right? If the pressures were equal, then the levels would be the same. You think about water in a hose, it goes to the same level on each side. Well, the fact that these levels are not the same tells us that the atmosphere is pressing down harder than the pressure of the gas inside this container is. So the gas pressure in here is less than the pressure outside, because they're having a pushing war. So the atmosphere is pushing down on this side, and the gas pressure in the container is pushing down on this side, and the gas in the container is losing. The difference in pressure is the difference in the heights of the columns of mercury. So whatever H is, you can measure it with a ruler. That's the pressure. The difference in pressure. So you have to know atmospheric pressure, and then you would subtract this amount, and that would tell you what the pressure is inside. In panel B, the pressure inside is greater, so in the pushing war, the gas in the container is winning over the atmospheric pressure. Oh, that was cool. I knew you could change color, but I didn't know you could change it while you were using it. We'll just stay with green. That's not green, it's red. Okay. So now the pressure out here is less. The difference in pressure is the difference in height of mercury. So the pressure inside equals the pressure outside plus this. Does that make sense? It's a very simple way of measuring pressure. They didn't have.
How do they change the pressure inside the container?
How do you change the pressure? That's a good question. The way this is shown, you couldn't get from, well, I'm going to take that back. You could increase the temperature. You could heat it up. Another way that this has been done is
why a thermometer works.
actually,
Will the name of mercury?
no, the thermometer works because the mercury, the liquid itself, expands with the temperature. So here's my very crude drawing. So you've got a gas in here. Those are gas particles. And here's your mercury. One way to increase the pressure in there is to add more mercury. So if you put more mercury in here, the mercury is going to push down, and this is going to go up, and this is going to go down a little bit. And so that's one way to increase the pressure. And this is how they did experiments. They had a gas. Let's just erase that whole thing because that's really ugly. I'm not an artist, and I never claimed to be one. Just not. Okay.
Are things like this used like in coal mines, in dealing with different pressures and gases at different locations in the earth, and what they might do? Or...
I don't know. I don't know if these are used in mining. So just a tube like this, if you start out, oh, that's way too high. If you start out with mercury like this, and here you have your gas, and in fact, we're going to talk about this. So here you have a volume of gas. You can measure its volume. If we add more mercury to this, then this is going to push down and this is going to come up, and now we're going to get a difference in pressure, and that's going to squeeze that gas and change its volume. And we're going to, I think it was, I forget their names, Charles, I believe, did experiments like this, where he changed the pressure by adding mercury to the tube, and then he measured the volume, and then he graphed it, and he figured out something that we call Charles' law. So there's a teaser for something that's coming up. Barometers measure atmospheric pressure. Manometers measure pressure in a container. This is a cool thing. One of these years I'll get my act together and actually do something like this. Collapsing can. So this is like a solvent can. You would want it to be really, really empty. Here's a Bunsen burner. You heat this can up with the lid off, and then you put the lid on, so you seal it, and you let it cool down. And as the gas cools down, it compresses, it gets smaller, and it'll actually pull the can in on itself. Very cool. It's very cool.
Does that happen a lot of different?
It would do, you could do this with lots of different things. You could do it even with a 2-liter soda bottle.
I've seen a 55-gallon drum.
Yeah, you can do it with a 55-gallon drum. It's pretty impressive. It's pretty impressive. But even a 2-liter soda bottle, if you have it empty, it's important that it be a gas, not the liquid. So it's empty, and maybe you submerged it in a pot of boiling water. You don't want to stick it in the oven because it'll melt. But you get it hot, and then you seal it up and let it cool down. Maybe stick it in ice water, and it'll crunch in on itself. It just doesn't make as much noise as the can does. Someday I'll get around to doing that. So we looked at some pressure units. We need to know how to convert pressure units, and this is dimensional analysis. Pardon me? Yes, dimensional analysis. I told you at the beginning of the semester, this is going to come back over and over and over again. Okay, so we don't have the table of pressures here, so I'm going to write it out real quick here. 1 atmosphere equals 760 millimeters of mercury, which equals 760 torr, which equals, let's see if I can remember this number, 101,325 pascals. Is that correct? And then there's a couple others. There's 14.7 psi. PSI is pounds per square inch. That's what we use when we measure the pressure in your tires. Pound is a unit of force. Square inch is a unit of area. Pressure is force over area. And then there's inches of mercury as well. The cool thing about the way that the tables of pressure unit conversions are set up is that all of these things are equal. And so we don't have to do multiple step conversions, because an atmosphere equals 760 millimeters of mercury, and 14.7 psi equals 1 atmosphere, so 14.7 psi equals 760 millimeters of mercury. You take any of these units and set them equal to each other, because they're all equal. So here, pressure of a gas is 2.5 atmospheres, and we want torr and pascals. So 2.5 atmospheres, and we're going to multiply. We just have to multiply by one factor. We want torr, so we multiply by torr, and we divide by atmospheres. Put the units in first. Atmospheres cancel out. What's the relationship? Well, 1 atmosphere equals 760 torr. So we have 2.5 times 760. And my calculator says 1900 torr. Well, that should have how many significant figures? 2, because of 2.5 atmospheres. The pressure, 1 atmosphere and 760, those numbers are exact. They're defined. The other ones aren't. So the best way to write this would be 1.9 times 10 to the third torr, because that's clear about those zeros. So what if we want to do pascals? Well, we could convert torr to pascals, or we can convert atmospheres to pascals. Let's go with atmospheres. This is a smaller number. 2.5 atmospheres times, and we want atmospheres on the bottom and pascals on the top. And they cancel out. Look in the table. 1 atmosphere is 101,325 pascals. We don't use pascals much at all in chemistry. We just talk about them and do conversions with them. And we stick to the units that we like. So this also should have 2 significant figures. My calculator is telling me 253,312.5. We don't know it that accurately. It ends up being 2.5 times 10 to the 5th pascals. You're like, wait, 2.5, but we multiplied by this number. Yeah, but that number was really close to 100,000, right? It's just not quite. Anybody curious why there are so many pressure units?
People wanted their name in science.
People wanted their name preserved forever. Actually, no. There are different units of pressure because people in different fields measure different sorts of pressure and do different sorts of calculations with them. And so if you're a physicist and you're using newtons and meters and doing all these crazy things that they do with their equations, and you want your units to work out real nice, you're going to use pascals or newtons per square meter. PSI, pounds per square inch, that's like an everyday sort of thing. And this, the pressure on your tire, it's like, 55, 35, something like that, a reasonable number, not 101,000, right? And so we tend to have units that are convenient for the field in which they're being used and that give us numbers of reasonable sizes. The 760 millimeters of mercury came about from the barometer and measuring the height of the column of mercury. So.
The homework talks about kilos and pascals. Why does that go into the metrics units for that one?
Okay, so pascal is an SI unit, which is essentially the same as the metric system. Okay, so pascals, you can also do kilopascals or decapascals or megapascals. You can use any of the metric units with pascals. So yes, I think there is some in the homework that has
What would they use
kilopascals.
that in what type of field?
Perhaps in engineering or physics. And I'm a curious person, but I'm not that curious.
I'll never.
You could Google it. There's a bunch of other units for pressure too, but
But it would work the same, right?
it'll work the same, yeah. Yeah.
Move the numbers around.
But we'll find for working with gases that we're going to want to use atmospheres at some point, just because of a constant that we're going to use.
It means the same thing, but you're going to get a different number.
You'll get a different number, yes, but it represents the same pressure. Just like if you measure something in meters or in inches. You measure a yardstick in inches, it's 36 inches. In meters, it's like 1.06 meters. Different number, but the unit's different. It's the same length. Okay, so the vapor pressure over a beaker of hot water, don't worry about the term vapor pressure, is measured as 656 torr. What is this pressure in atmospheres? Well, let's do some just general thinking before we do any calculating. 656 torr, is that more or less than 1 atmosphere? It's less. So answer A cannot be correct. So 656 torr, if we want to convert that to atmospheres, we're going to multiply by atmospheres and divide by torr. 1 atmosphere is 760 torr. I will give you all those pressure conversions on an exam, but if you remember the 760 torr or 760 millimeters of mercury to 1 atmosphere, you'll save yourself some time because we're going to use that a lot. So this comes out to be 0.863 atmospheres. So then B is the correct answer. Any questions?
It's above sea level a little bit.
Well, probably yes.
Sea level's 1.
Yeah.